Uh, Next topic we're going to look at real quick. I'm not going to spend a lot of time on it, but it's called the Zeroth Law of thermodynamics, which is the basis of temperature measurement. Basically, when a body is brought into contact with another body that is at a different temperature, heat is transferred from one body at higher temperature to one at lower temperature until both bodies attain the same temperature, right? Thermal equilibrium. This is the zeroth law. Basically, zeroth law states that if two bodies are in thermal equilibrium with a third body, they are also in equilibrium with each other. The reason why this cannot be concluded from the other laws of thermodynamics, and it serves as a validity of temperature measurement. Temperature that we're going to be looking at, we're going to be looking at an absolute temperature scale, right? A scale that is independent of the properties of the system. So you may have heard of Kelvin, right? Kelvin is basically Celsius, the temperature in Celsius, plus 273.15. And if you realize that the change in temperature of Kelvin is the same as that in Celsius. That's for SI units. What this slide doesn't have that I'm going to write in is in English units. Actually, we get temperature in Rankine is equal to temperatures in degrees Fahrenheit plus about 460. It's actually 459 point something. I don't remember off the top of my head what that exactly is, but the same principle is that the change in temperature in Rankine is equal to the change in temperature in degrees Fahrenheit. So Rankine is the Fahrenheit as Kelvin is to Celsius. All right, the last section that we're going to be dealing with before we get to our example problem is the concept of pressure. I'm sure you guys have dealt with this before, so this is a review. If it's not a review, then great, we're going to cover it here. Pressure. Pressure is a force exerted by a fluid per unit area. So there's absolute pressure, which is pressure, actual pressure at a given pressure. So absolute pressure basically is measured relative to an absolute vacuum, absolute zero pressure. And then there's gauge pressure, right? So for example, if I have a gauge and I were right now in 1 atmosphere in a classroom were to measure the gauge pressure of the classroom, it would be 0. But of course, the pressure in the room is not 0. It's actually going to be 1 atmosphere. Gauge pressure is the difference between absolute pressure and the local atmospheric pressure, right? So gauge pressure would be absolute pressure minus atmospheric. So if you look, this is a great diagram that kind of illustrates the differences between absolute pressure and regular pressure. So let's say that this is atmospheric pressure. This line represents absolute pressure. This line represents a vacuum, right? So the difference between atmospheric and the vacuum would be atmospheric pressure, and the difference between atmospheric pressure and the pressure you're measuring is gauge. Then the difference between what you're measuring the pressure of and vacuum would be absolute pressure. And really, all pressure is measuring the depth of a fluid, right? So for example, you're feeling 1 atmosphere of pressure because you're feeling the weight of the atmosphere above you, the weight of all the gases that constitute our atmosphere. There's a certain height of that gas, of that what we would call fluid, that causes you to feel that pressure. Let's look at a different example of it. Let's say I have this fluid, right, and I'm trying to measure the pressure at this depth. It's basically a force balance, and the force balance tells us that the pressure difference between 2 points at 2 different depths is equal to the height, the height difference between the 2 points you're measuring the pressure of. So if I were to go above the atmosphere to the point that we would state that the atmosphere of the Earth is no longer occurring, at this point, we would have a certain altitude, right? A certain altitude with 0 pressure would occur versus the pressure we experience here. So if you were to take the density of an average density of the air in the atmosphere times gravity and multiply it by that height, that should equal 1 atmosphere. In differential form, right, we get that the change in pressure over height is equal to negative rho g. So if the fluid is compressible, like air, You actually have to integrate that over the two different points at which you're at. But in general, the variation of pressure with depth is significant for, is significant for liquids and negligible for gases. So you probably heard of a manometer. A manometer is a device. If you haven't, a manometer is a device that's used to measure the pressure of, for example, a pressure vessel. So let's say I have a tank, there's gas in it. The tank is going through this tube, pushing on another fluid, causing the fluid to have a height here. This height is representation of the pressure inside the tank. So if I have the pressure inside a tank has to equal atmospheric pressure, right? This is atmospheric pressure pushing down here. Pressure inside a tank has to equal atmospheric pressure plus the pressure caused by the height of this fluid. And sometimes there's more complicated manometers that have several fluids one after another, but this is the basic premise on how it works. And it's also the premise on how a barometer works, right? I have here mercury and a tube where it's filled with mercury and put upside down into here such that this is pretty close to a vacuum, right? So what happens is I have atmospheric pressure pushing down on top of this pool, pushing the mercury up into this column, causing the height difference. So if I assume this to be a vacuum, that means that this atmospheric pressure pressing onto this pool of mercury, causing the mercury to go up inside this test tube, well, that pressure has to equal the rho GH, the height of that fluid. All right, I hope this is clear. We're going to do an example problem, but before we get to the example problem, I just kind of want to go over the basics of how we're going to be doing problems and how we are going to be grading them. So when you guys do your homeworks for this class, there's going to be three basic parts of the problem. One is going to be you indicating a schematic with all givens and what you are solving for, right? So a schematic of the problem, indicating the givens that you are given. So if appropriate, give a schematic of the problem. If there's no schematic to draw, simply write not applicable. But be sure to list all the givens in the schematic and indicate what you are trying to find. Then there's going to be assumptions, right? In order to solve thermodynamic problems, you're going to have to make varying assumptions as you go along. So state all assumptions associated with the problem, and then your analysis is worth 75 points. This is where you include all the work that goes into solving the problem, and be sure to circle your answer. So just to illustrate that, let's go ahead and do an example problem together. Right, so here I have the problem statement states that the barometer of a mountain hiker reads 930 millibars at the beginning of a hiking trip and 780 millibars at the end. Neglecting the effects of altitude on gravitational acceleration, determine the vertical distance climbed. Right, so, and then assume the density of air to be 1.2 kilograms per meter cubed. So let's start with a schematic. On the schematic here, let's this is my ground. I have my hiker hiking up a mountain, right? So here's my hiker, not to scale. It's telling me that at the top of this mountain, I have a pressure of 780 millibars. Down here, I have a pressure of 930 millibars, right? The pressure difference caused by me climbing is due to the fact that I have less atmosphere above me at the top than I do at the bottom. So what height makes that pressure change? Right, so the first step is to list some assumptions. And there's not much to list. We'll assume, for example, according to the problem statement, that gravity is constant. And we'll also assume that the density is constant, right? I mean, as we go higher, we understand that air becomes thinner, so the density would not be constant, but we'll assume the case that the density is constant, right? So based on those, we'll go ahead and try the example problem. Good practice would have you guys try the example problem on your own. So if you want to, you can actually go ahead and pause this video at this point. If you have the notes, you can go ahead and try the example problem on your own. If not, you can just continue watching and I'll walk through the solution. So I'm going to go ahead and start walking through the solution right now. We'll go to the next slide. So the analysis. The analysis is stating that the pressure difference between the bottom, right? We always have to write in the equation. So we have to work through the form of the equation. Now, there's not much to work through. The pressure difference between the top and bottom has to equal the rho GH of the air, right? Normally, what you would do is that you would set up the basic model of the equation and then work through the final form of the equation for that problem based on the solutions. But for this problem, it's not really necessary to go through that. So if my initial pressure in the bottom was 930 millibar, that's equal to 0.930 bar. And then the pressure on the top was 780 millibar. That's equal to 0.780 bar. So as I go through it, I'm going to fill in the blanks. I get that the pressure on the bottom, 0.930 bar minus 0.780 bar equals density of air, 1.2 kilograms per meter cubed, times gravity, 9.81 meters per second squared, times h in meters. Now, I can't leave it in this form, right? Because what I have here is, here I have bar, and I don't have bar on this side. So in order to make sure my units are consistent, I have to multiply this whole equation by where I have 1 Newton is 1 kilogram per meter second squared. And then again, I have 1 bar is equal to 100,000 newtons per meter squared. So if I go through the math, which I am not going to take time to work through every single piece of algebra, if I take this and I solve for h, I would get that the height the climber went was 1,274 meters. Okay, so you can see the analysis starts with the equation. I throw in my knowns. I make sure that I have my proper unit conversions, make sure I'm in constant units, and then I solve and I get 1,274 meters. And that pretty much ends this chapter. You'll see that there's a homework in the appropriate place for you to look at, and you can go ahead and start that homework for this chapter. And this ends the video for chapter 1.